Start recording. So we're going to see how these models of the atom actually grew. Thank you very much.
Oh, I found this in the thing. Do you want me to put it back in?
You can put it back there, yeah. Thank you, Zelin. Okay. This is page 11. Page 11. Sorry? Yes. Are we all on page 11? Does anybody need a book? Zelin, you have a book? For unit 2? Okay, perfect.
In this video, we're going to talk about how J.J. Thomson discovered the electron in 1897 using the cathode ray tube experiment.
Okay, let's make this volume a little higher here.
So these days, we think about atoms kind of like this. They're made up of a variety of smaller subatomic particles. But in the late 1800s, it was all about John Dalton's model of the atom. In the early 1800s, John Dalton had proposed that all matter, all stuff, was made up of tiny, indivisible particles called atoms. At first, not many people believed him. But throughout the course of the 1800s, more and more scientists got on board with his idea. But it remained an open question whether the atoms were really indivisible. Were they like tiny little billiard balls, hard and solid? Or were they made of smaller things? No one really knew the answer to that. But J.J. Thomson was able to answer part of that question when he discovered the electron. He discovered that it was much smaller than atoms. He discovered that atoms had electrons. And so he was able to say for the first time that atoms weren't totally solid and indivisible, but they were made up of smaller, subatomic particles. Let's look at how he discovered the electron. So Thomson used what's called a cathode ray tube. It's a big tube of glass that's kind of like a bottle. You can imagine it sort of like this soda bottle. It's sealed.
And for this one, just like the last video we did, if you want to write down as we go, that's fine. But we're also going to write down together at the end. So don't stress if you miss something. Yes? Yeah, Tyler spelled it wrong. So it's without a P, but if you spell it with a P, I don't care. Yeah? So Thomson shouldn't have a P, but if you spell it with a P, it's okay.
So Thomson connected these two pieces of metal to a power source, and here's what happened. A ray shot from this piece of metal across the tube and created a glowing spot over here when it hit a special coating on the inside of the glass. Now, Thomson didn't know what was going on, but what really was going on is that electrons from this piece of metal were shooting out. They were attracted to this piece of metal, which has an opposite charge, but they were moving so fast that they shot all the way across the length of the tube. Anyway, Thomson sees this ray, and he gets curious as to what it's made of. And so he asks the question, the stuff that the cathode ray is made of, does it have an electrical charge? And here's how.
Do you guys know what the two electrical charges are? There's negative and there's positive. Yes. So he's wondering, Don't worry if you can't see it, we'll go over it later, okay? It says power source. He says, is this ray positive? Is it negative? And I really cannot talk over you today, okay? I'm kind of getting over a cold here, so please don't make me raise my voice anymore because otherwise I'll have coughing fits by the end of the day. Hi, thank you so much. So he's wondering, is it positive, is it negative, or does it have no charge? So we're going to see what he does to figure that out.
He attempts to answer that question. He takes two metal plates and puts them on either side of the cathode ray tube. And then he turns on electricity, which makes the top plate positively charged and the bottom plate negatively charged. And check out what happens to the cathode ray. When he turns on the power, he sees that now instead of going straight through, the cathode ray bends up. It bends up towards the positively charged plate.
Do you guys know what positive and negative charges do to one another? Yeah, positive and negative attract. Opposites attract, exactly. Do you know what positive does to positive? It repels. Do you know what negative does to negative? It repels. So I'd like you guys to think, this is being affected by the positive charge here and the negative charge here. Discuss with your neighbor what charge you think this green ray is. Is it positive or is it negative? What charge is that green ray? Okay, let's find out if your ideas were correct.
So based on this, he reasons that the cathode ray must be made of stuff that's negatively charged.
Did you guys get negative? Negative. Oh, why is it negative? If this beam is negative, what is it bending towards? It's bending towards the positive because the negative is attracted to the positive. It's bending away from the negative because negative repels negative. So that was kind of a clever thing that he did in that experiment. He's like, let's see what happens. Maybe nothing would have happened, but it did. So he figured something out. He figured out that ray is what charge? Negative. Okay.
Since it's attracted to the positively charged piece of metal, and he knows that opposite charges attract. But just because he wants to be very careful, he's a very careful guy, he tries to check this another way. So he uses a magnet. If something has an electrical charge and it's moving, a magnet will push it in particular directions. So he takes a cathode ray tube, if you want to think that this marker is kind of the cathode ray tube, and he surrounds it with a magnet, just like this. We can kind of show what goes on by slipping the magnet under like this. So anyway, he puts the magnet here, and he sees now that the cathode ray bends in the other direction. It now moves downward. Now, if the cathode ray is indeed negatively charged, this is exactly how he would expect it to move in the presence of a magnet like this.
So he's just confirming his results. If you actually want to understand why and how a magnet makes a moving charge attracted or repelled, you would want to take physics, okay? Because they do that in physics 12. For now, you can just say, hey, this confirmed that this was negative.
So this is just further confirmation that whatever makes up the cathode ray probably is negatively charged. So he takes the data that he gets from these experiments and he's able to draw a few important conclusions about cathode rays and what makes up atoms. Okay, so based on the outcomes of the experiments with the charged plates and the magnet, Thomson is able to conclude that cathode rays must be made of stuff that is negatively charged. Okay. He combines the information that he got from the experiments that I just told you about with some other data that he collected. And he's able to come to the conclusion that the particles that make up cathode rays are 1,000 times smaller than a hydrogen atom. Hydrogen atoms are the smallest atoms.
Okay, so now how did he do that? We're not going into that here. He did some other experiments and he figured out these particles are 1,000 times smaller than the hydrogen atom. What's special about a hydrogen atom? Hydrogen atoms are the very, very smallest of all the atoms. So these particles are 1,000 times smaller than the smallest of atoms.
So this thing that's in the cathode rays must be really, really tiny compared to an atom. And finally, Thomson swaps out the type of metal that's in the cathode tube.
So maybe right now, those are made of iron. Okay? That could be the metal they're made of. He's going to now take it, and instead of having iron, maybe he puts in some copper or some zinc. Okay?
He uses a variety of different types of metal, but he finds that all of the different metals he uses give off the same cathode rays, and regardless of what metal he uses, the size of the things that are in the cathode rays is exactly the same.
So where is the cathode ray coming from? Take a look at the picture. Where is the cathode ray coming from? It's coming from, what's that thing there? That is, what's that round thing made of? That round thing is a piece of metal, okay? No matter what metal, cathode rays come out of there. That means that whatever the cathode ray is made of, comes out of every metal. That means every single metal contains whatever is in cathode rays.
So based on these three conclusions, he's able to come up with the idea that atoms have tiny, negatively charged particles inside them, and these things that we're talking about here are electrons. Now, if you're like me when I first learned this, you might be confused how these conclusions definitely tell him that there are electrons inside atoms. I remember when I first learned this stuff, I was thinking like, wait, doesn't this just show that electricity or cathode rays have negatively charged stuff? How does this tell us anything about the atoms? Okay, here's why. At the time that Thomson does his experiment, everyone, for the most part, agrees that all things are made up of atoms, that atoms are the smallest things that make everything up. They're like the smallest things in the universe. So if Thomson is able to show that there are even tinier things, well, where are those tiny things coming from? They have to be coming from atoms because everything's made of atoms, right? That's the only place they can be coming from. And even if electricity, even if you want to say that, oh, well, he's just showing that electricity is made of electrons, well, then still, where are the electrons coming from that make the electricity? The electrons have to be coming from other atoms. And since he can move or remove these pieces of metal and swap other metals in and he still gets electrons, it again shows that all different types of atoms are able to release or give off electrons. So they must be in there to begin with. Anyway, these conclusions that Thomson comes to have dramatic effects on how scientists think about what the atom actually looks like. Now, at the beginning of the video, we said that in Dalton's atomic model, atoms are indivisible, that they're not made of anything smaller. But
so this is the first model of the atom. And if you're wanting to retake the quiz because you were like, oh, dang, today did not go so well, because I think that was the case for quite a number of people, probably after the test, you were like, oh, I didn't really hear Ms. Spence say that there was a quiz on Monday, you know, because it was after the test and it was, you know, like just a lot of stuff going on. We are going to take a look at how these models were discovered. I would actually recommend waiting until after we've done this, and then you'll have more exposure to the models and you'll be able to retake it at that point. Does that make sense? Yes. Can you retake it now? Oh, you didn't take it. Can we wait until we're done this? Yeah. Yeah, perfect. Yeah, you can definitely take it today. You'll take it tomorrow? Okay, cool.
when Thomson discovered that atoms have tiny negatively charged electrons inside them, he essentially disproved this model, at least the part about the indivisible atoms. So here is the model of the atom that Thomson comes up with. He realizes, first of all, that electrons are negative. We already talked about that. But then he notices that on the whole, atoms in general are usually electrically neutral.
So he said, in the atom, there's negative things. But atoms are not negative, they are neutral. What has to be there for an atom to be neutral if it contains negative things? There has to be the same amount of positive things so that it all equals out to 0.
So even though they have these negatively charged electrons inside them, the atoms as a whole don't have a charge. So Thomson realizes that in order for the atoms not to have a charge, there must be some positive charge in the atom that can balance out the negative charge of the electrons. And then the positive and the negative balance out, and the atom then as a whole doesn't have a charge. So he comes up with a model that he calls the plum pudding atom. Now, plum pudding is kind of a British thing, so if you're American, it might be better for you to think about this as like the blueberry muffin model. And here's how it works. Thomson imagines that the atom is like a blueberry muffin, and that electrons are stuck in this atom the way blueberries are stuck in a blueberry muffin. So you have these little electrons that are stuck in the atom, but then they're surrounded sort of by a dough. And the dough, like in a blueberry muffin, keeps these electrons or blueberries held in place. But the dough itself has a positive charge. And it's that positively charged dough that is what balances out the negative charge of the electrons. And so together, they don't have any total net charge. So the atom is electrically neutral. So that's how J.J. Thomson's discovery of the electrons leads to this plum pudding model of the atom. But now J.J. Thomson didn't have it quite right, because it turns out that the positive charge in the atom isn't sort of spread out in this dough or.
Do you guys remember the atom from last year? Anyone remember where the positive charge is? It's actually in the middle, but Thomson didn't know that. They had to do some more experiments to figure that out.
Pudding, but instead it's concentrated right in the center of the atom where the nucleus is. So that's going to be the next step in discovering what the atom really looks like. If you're interested in how scientists disproved J.J. Thomson's plum pudding model, check out Rutherford's gold foil experiment, where he discovers that atoms have a very small, very dense, positively charged nucleus.
Okay, and we're going to take a look at that next day. But for now, let's go and fill in everything together. Okay, so starting on page 11, and you can fill it, Brooklyn, you can fill it in and you can take those pages out. Okay, and take them home with you. So, the cathode ray tube experiment, who did it? J.J. Thomson. Whoops. J.J. Thomson. So how did we get from Dalton's billiard ball model, which just is an indivisible sphere, how did we get from there to this thing where we have protons, neutrons, and electrons? How did we do that? Right? That's crazy. You don't need to have this labeled, but that's what we have eventually ended up with. It all started with J.J. Thomson and his cathode ray tube. What is this tube called? It is called a cathode ray tube. What are those two circular things? Those are pieces of metal. What is the cathode ray tube made of? It's made of glass, and they sucked all the air out of it. So there's nothing in that tube. There's no air, no nothing, just the two pieces of metal. Okay, so nothing in there except for the metal. So then he hooked up those pieces of metal to a what? Power source. So he hooked up the pieces of metal to a power source. And wow, what did he see? Literally, he saw a glowing green ray. No. What do we actually call that glowing green ray? It's called a cathode ray. So the cathode ray is the glowing green ray. So out of the first piece of metal shot a green ray called a cathode ray. And J.J. Thomson knew something about charges. He knew, just like you guys know, that opposite charges do what? Attract. And like charges repel. So you can see we've got a positive and negative attracting, and we've got the positive repelling positive, the negative repelling negative. He thought maybe the cathode ray has a charge. So he put a positively charged metal plate here. So this one's positive. And he put a negative metal plate down here. And the cathode ray it bent. Which direction does it bend? What does it bend towards? Towards positive. Also, it bends away from, what does it bend away from? Negative. If it bends towards positive, away from negative, what is its charge? Has to be negative. Sorry, I've been talking too much.
Have the ones that you gave last time.
Thank you. K95 mask. Taped to my face.
Just sit down.
Good. Do the enriched questions, but if you like don't get them, it's okay to leave them. Okay. Can I have it's now? I can do it fast. Yes. Yeah. So sorry. Oh no, don't apologize. All right. Well, that's the practice, but it doesn't matter. It's the same dang thing. Okay. There you go. Thank you. I put the test. Perfect, yes, you get to keep that one though. Okay, and this one I will take. Thank you. Perfect, thank you. Thank you.
You're right. Sorry, I apologize.
Awesome.
And also, I don't be playing just retro games. You're damn right. I only play retro games. Yeah, I played. It's over. It's like once for a party. The a single round of Columbus Black Ops. I haven't played it. Besides, I had Call of Duty. I had Call of Duty. Okay, I had Call of Duty World War, but I only ever played the campaign. Real. I never played it. I'll be. I had a copy of Black Ops 1, but I couldn't play it anymore because something happened with the disc and like my 360 just wouldn't read it anymore. So that's what. Are you doing like a 360 ever got the memory enough? No, it was like a 360 after that. The fact. You're just newer. Okay. I'm pretty sure it was like one. It was like one. Problem. It's over, man. Nope. But that's my school. God. I just finished a test, so I'm not sure my things for. So I was not.
Okay, good.
We don't have any final or midterm for this class.
You don't have any final or midterm?
He's ready to go. I think the
You don't have a plan, right? You got cancer.
Hey.
Yeah.
I have 2 tests on Friday.
Yeah.
I thought we were gonna have another one for chemistry.
Oh, it is. Quiz 2.3.
Oh, right.
Friday, March 6th. We have short day on Friday.
Okay.
Quiz.
Bro, I want
I
to
have a health test, and
Yeah, I'm gonna drop Xbox.
When I have a health test. When is that? Friday the 13th. I know. And I have a physics test that day too. I have a chem test that day. I was like,
It's Friday?
Or is it Friday?
so I'm saying, it's like, I said that. That's even worse.
No.
Okay, I won't be sick on my phone.
You
It's not a test, right?
Yeah. Oh, it's fine. So that was great to be.
Okay, I think it's like a very bad disease and skip their whole year and then come to final.